Chapter 8. Lab is dealing with Chapter 8 material. So Chapter 7, I want to talk about the conversions here for Chapter 7. So the types of conversions that we can do gram to mole conversion. Mole is just the quantity amount, and so it would be like, going from something to dozens or whatever. But here we would need the molar mass, mm, to do this. In fact, we need to invert the molar mass to do it, and so just put it in quotation marks. And likewise, we can go backwards, moles to grams. And then from moles, we could go to number of units using Avogadro's number. Or we can go from number of units to moles. Now, there are a few other things we can do. When we know the composition, we have formula conversions as well. And let's talk about the formula versions. An example would be like H2O. For H2O, there are a couple of things we can do. So the types of formula conversions we could do are like 2 atoms of H for every 1 molecule of H2O. So we have 2 hydrogen atoms for every molecule of H2O. We have 2 hydrogen atoms for every oxygen atom. Or we have 2 moles of H atoms for every 1 mole of H2O molecule. And so when I read this, 2 moles of H atoms for 1 mole of H2O molecules, it'd be like the same thing. It would be like 2 dozen H atoms for every 1 dozen H2O molecules. It's just a number conversion, that type of thing. Etc. And so we can generate a whole bunch of these from this. And so we can do just a quick example here of something. Calculation. And so I might be curious, how many hydrogen atoms can I find? Well, actually, let's start off with this. In 1.00 grams of H2O, how many molecules? Would I expect to find? And so here, when we're doing this, we go 1.00 grams of H2O. Then what we want to do is we want to figure out, how many moles of H2O that is. And how many moles of H2O that is based on the molar mass. Oxygen has a molar mass of 16. Hydrogen's 101, 1600, so altogether it comes out to 18.02. 18.02 grams of H2O is equivalent to a mole of H2O. This comes from the definition of the mole and the definition of the atomic mass unit. And so in exactly 1 mole of water, there's approximately 18.02 grams of water. And then we know that for every 1 mole of water, there's going to be 6.022, this is Avogadro's number, which we just memorized, 6.022 times 10 to the 23rd molecules of H2O. All right, and so we would do this calculation and then see how many water molecules. It's going to be a huge number because if you look at this, this is 1, this is 10 to the 23rd, this is about 10, and so it's going to be a huge number. So let's take a look at what it comes out to. So I'll just do 6.022 times 10 to the 23rd divided by 1802. And this comes out to 3.3. Now I'm allowed, this is 4, this is 4, this is 3, so I'm allowed 3 sig figs. So I get 3.34, and then I'll subscript 1 extra. 3.341 times 10 to the 22nd molecules. That's a lot. All right, so we can figure out how many molecules there are here. We can figure out how many moles there are. We could also figure out how many atoms there are. To figure out how many atoms there are, let's say how many atoms of hydrogen are present in that. And so we'll just continue with this example here. If we want to do the how many atoms of hydrogen, well, you know, we could take this number, if we know how many molecules there are, it's twice as many if we double this. But to avoid round-off error, we'd probably just start it over, the calculation, because there's more digits, you know, 3, 4, 1, 8, etc. You could change it. And so normally I just start these over. 1.00 grams of H2O, and then go from gram to mole conversion. This gram to mole conversion is very common in chemistry. 18.02 grams. The reason a gram to mole conversion is very common is because of this. Chemical formulas like this are not written as mass ratios. For example, this is not 2 grams of hydrogen for every 1 gram of oxygen. Chemical formulas like this are written as atom ratios. And so 2 atoms of hydrogen for every 1 atom of oxygen. Okay, if we know the atom ratio, then we know the mole ratio because it goes like this. 2 atoms of hydrogen, 1 atom of oxygen. 2 dozen hydrogen atoms, 1 dozen oxygen atoms. 2 moles of hydrogen atoms, 1 mole of oxygen atoms. And so chemical formulas like this are always atom or mole ratios. We use the terms interchangeably, so when we look at a ratio like this, we're always thinking, okay, this is the atom ratio or it's the mole ratio. You know, it's just a ratio of numbers. And therefore, since all our formulas are atom or mole ratios, you know, then we usually do a gram to mole conversion because, you know, if I have 1 gram of water, I want to put that into terms I know in terms of composition. And so this is one of the most common conversions. So oftentimes we stop here, gram, and then figure out how many moles. Moles is the quantity, you know, of a water molecule. It depends on how much a water molecule weighs. A water molecule weighs 18.02 U per water molecule on average, or it weighs 18.02 grams if I have a mole of water molecules. That's the parallel relationship in mass. We call one the molecular mass. The molecular mass is U per molecule, and we call the other the molar mass. The molar mass is grams per mole of molecules. So we're using the molar mass here, grams per mole, and invert it. We always invert it just because, well, it doesn't really matter. We use it whichever way it cancels out the units. Or in this case, it cancels out the units if we invert that. But the ratio is the same. Okay, then from moles, we can actually go to an individual number of units. That is, we can do this. There are different choices. We can go from moles of water to moles of hydrogen. And that's typically what we would do here. We would go, for every 1 mole of H2O, there are 2 moles of H atoms. Again, this is like saying for every 1 dozen water molecules, there are 2 dozen H atoms, because moles is a counting unit, just like a dozen. And then for every mole of H atoms, we have an Avogadro's numbers worth of atoms. So 6.022 times 10 to the 23rd atoms. well, I still have the number in my calculator, so I'll just do it times 2. This gives us 6.68 sub 3 times 10 to the 22nd H atoms, etc. So we could do other calculations. We could figure out how many oxygen atoms are in a gram, that type of stuff. Or given the number of grams, we can do branch off to a lot of different directions. In the future, we're going to do more of these types of calculations. These calculations are called stoichiometry calculations. Stoichiometry calculations are just quantity relationship calculations. Also, we can figure out how much this weighs. You know, if I had 3.341 times 10 to the 22nd molecules, how much does that weigh? Well, I can get the weight in U, or I can get the weight in grams. Well, the weight in grams would be much more beneficial because it's such a huge number. This would be a huge number of U. All right, so the formula is very important, and we're looking at the formula. And so how are these formulas determined? You know, how are these formulas determined? And so let me talk briefly about determination, because the formula is very important. We want the atom or mole ratio here. And so the formulas are very, we don't want the mass ratio. You know, the mass ratio, what is mass ratio? You know, and so we have different ways of representing the composition. Composition, the formula is the atom or mole ratio. And then we have the percent composition. The percent composition by mass. Okay, we can also have the percent composition by atoms. Which we could get, you know, the percent composition of H2O by atoms is, it's 2/3 hydrogen, 1/3 oxygen. And so we just convert 2/3 into percentage by multiplying it by 100%. 1/3, and so it comes out to 67% hydrogen, 33% oxygen. You know, it depends on how many sig figs we want. We can go more. But as far as mass goes, you know, the percent composition, percent of A is equal to the mass of A over the total mass times 100%. And so that'll give it to us. And so the mass of A, well, this is it. We'll do water again. What we're going to do is we're going to assume we have 1 mole. So just assume 1 mole. If we have 1 mole, then we have 18.02 grams of H2O. Because that's the molar mass. If we have 1 mole of water molecules, it's going to weigh that many grams. It's a lot of water molecules, so that's why the mass adds up. And so out of that 18.02, this is it. We can get the percent hydrogen. The percent hydrogen equals this. Well, how many grams of hydrogen? It would be 2 times the mass, molar mass of hydrogen. And so the molar mass of hydrogen is 1.008, you know, because we want 4 sig figs here. So 2 times 1.0, or 1.01, you know, if we want 2 decimals. But in this case, it's standalone. Okay. Divided by 18.02, which is the total grams of water. And so this is how many grams of hydrogen I have. Each mole of hydrogen is going to weigh that amount, so we're going to get 2.016 over 18.02. This is times 100%. Times 100. So it comes out to 11 or so. Let me see what it comes out to here. So 2 divided by 18.02. Actually 2.016. So 2.016 divided by 18.02 equals my calc. 18.02. 11.18. 11.18, we're allowed 4 sig figs, so I'm going to carry 1 extra. 11.187% hydrogen. And then the percent oxygen, just be 100% minus this. There's only 2 components, so I could do, they're different calculations. I can just repeat it. I could do 16.00 grams of oxygen for every 18.02 grams of H2O times 100%. But I know that there are only 2 things in here, so if it's 11.187, then the remainder has to be oxygen. So it could be 100% minus 11.187. I'm just going to do that because I already have it in my calculator. Rather than, it comes to 88.812% oxygen. Now, we don't use mass ratios when we do this, because using mass ratios is not nearly as useful as using atom or mole ratios to represent the composition, because if I were to represent the composition using mass ratios, it would look something like this. Comp by mass ratios. In a more compact form, obviously we could just leave it like this here, but in a more compact form we would write H, we have 11.187, 11.18 sub 7, O, 88.812. All right, now we don't have to do a gram to mole conversion. Now we could just use the mass ratios, but are these mass ratios, are they very useful? Because when you look at this, this is just a 4 sig figs. Is this an exact number? No. Not even close. And so the mass ratio, yes, we could use it, and we do use it. There are times when mass ratio is quite useful, but we much prefer atom or mole ratio, right, in representing composition. Now, the formula is very important because the formula allows us to do these types of stoichiometry calculations. Stoichiometry calculations is a big emphasis in chemistry because, if you have this many grams, how many atoms, how many molecules, how many moles, that type of thing is very important. But the other thing that's very important is if you know the composition, for example, it's H2O versus H2O2, what else can we get from that? We can get, we're just not always interested in numbers. We're also interested in the behavior of it, and what can we get from the formula? We can get an idea, a feel of how it might react chemically. How it could react. And so the formula gives us insight into the chemical properties for sure, because composition, structure are all interrelated to properties. And so what we want to do is we want to figure out what is the composition. We want to know the composition of everything. And so how are our formulas determined? When I say how our formula is determined, how is the composition determined? So let's say I have some unknown liquid here. I want to know what is the composition of this unknown liquid. How would I determine that? Can you tell me what the formula for this is? Probably because it came from there, but if you didn't see me pour from the tap, can you tell me what the formula is? It's just some liquid, right? And so how are formulas determined? Okay, composition is often determined like this. One, you have some unknown. And you don't know, is this unknown a mixture or pure? So mixture or pure. Sorry, that's small. So we have some unknown. Is a mixture or pure? So what we try to do is we try to separate, isolate purify. So if it is a mixture, we try to separate the components of the mixture into individual substances, which would be elements or compounds, isolate those and purify them. Then what we do is we test the properties individually. Okay, so A, we test properties individually and try to match with known substances. And so, you know, you could go to Wikipedia, you could go to the CRC Handbook of Chemistry or Physics, you could go to the Merck Index, and there's a huge compilation of known compounds and their properties. And so you try to match it. So for example, well, this is often done. One of the quick rapid tests is if you already have a kind of an idea of what it is, then you can try taking its melting point. You know, usually melting point's not so difficult to measure. You take its melting point and see if you can match the melting point. So for example, or boiling point if it's a liquid. You know, so what we do is we might boil this liquid. If it boils at 100 degrees C, then wow, I have a suspicion that this must be or might be water. I wouldn't say must be, because there could be other things that boil at 100 degrees C. And so what I do is I test additional properties, right, until I can narrow it down to a small number of substances or one single substance. And so this is what's done. But what if you synthesize something new? Let's say, you know, and chemists are synthesizing new compounds all the time. And so if you synthesize something new, how do you know what its composition is? And so this is what you do. B. You know, sometimes the properties you aren't going to match it with anything because it's something new, or maybe that it's not in the database of stuff. And so the other option is you send it out for chemical analysis. There's examples of this. Let's say one example is elemental analysis. There's ways to test for individual elements and to see how much of that particular element there is. But it's expensive, of course, you know. And so you want some idea, because you don't want to test for the entire periodic table. If you test for the entire periodic table, it's not doable. And so you have to narrow it down, you know. And you have an idea of what elements there might be present, and then you send those out for analysis. Another example would be sulfate. Like, you know, you test for an individual ion, like how much sulfate is present in this sample. You know, sulfate analysis, fluoride analysis, etc. So you're testing for individual species like this. Another one is if it's combustible, you know, we have something called combustion analysis, where you burn it. And based on how much CO2 is formed and how much water is formed, you can figure out, you know, how much. Combustion analysis is for, you know, carbon, hydrogen, organics. Let me see. Carbon, hydrogen, oxygen, nitrogen, phosphorus might be present. And so when you send out a sample for chemical analysis, what you get back is not the atom or mole ratio. What you get back is the mass ratio. And so let's take a look at a problem here. All right, so let's say we send out a sample, and whatever what we did was we separated and isolated and purified a sample for chemical analysis. So we sent the sample for chemical analysis, and we'll just say it's an unknown sample sent for analysis. And this is the result that we get. After it costs money for this analysis, but what they determined, there was 74.1% carbon. And so the sample contained 74.1% carbon, 8.64% hydrogen, and 17.3% nitrogen. 17.3% nitrogen. And so what we do is this. This is the by mass ratios. And so if we look at the by mass is not so helpful here. And so what we want is we want the atom or mole ratio. And so what we'll do here is we're going to just convert this or figure out what the atom or mole ratio is by just using the molar masses. So what we're going to do is we're going to assume 100 grams. If we have 100 grams, then we're going to have 74.1 grams of carbon, 8.64 grams of hydrogen, and 17.3 grams of nitrogen. And then we're just going to convert it to moles using the molar mass. And so converting it to moles, we'll just do them individually here. And so here, to convert this grams of carbon into moles of carbon, we'll use the molar mass off the periodic table. There's 12.01 grams of carbon for every mole. And so a mole of carbon atoms weighs 12.01 grams. One carbon atom weighs 12.01 U. For hydrogen, we're going to use this one. A mole of hydrogen weighs, normally I use 1.01, but in this case I need more digits, so I'm going to go 1.008 grams of hydrogen. And for nitrogen, a mole of nitrogen weighs 14.01 grams. And so we're going to just convert that into moles. And so I converted into moles. Let's go with 74.1 divided by 12.01. .16. So up here I get 6.16, and I'm allowed 3, so I'll carry 1 extra. 2 moles of carbon. And then here I'm going to get 8.64 divided by 1.008, 8.57, 1 moles of hydrogen, and then 17.3 divided by 1401 gives me 1.23 4 moles of nitrogen. Now, formula is an atom or mole ratio. So we have the formula here, but it doesn't look like a formula. And so we convert this into a formula. It's going to be carbon 6.162, hydrogen 8.571, and nitrogen 1.234. Well, this looks just as bad. When I look at this mole ratio, this looks just as bad as the mass ratio. And so what I need to do is in terms of moles, this is fine, but in terms of atoms, is it possible to have 6.16 atoms? No. And so what I'm going to do is I'm just going to convert it, and thinking in terms of atom ratio here, I'm going to convert it into whole numbers. And so what I'm going to do is I'm going to divide by the smallest number. which is going to be 1.234 in this case. And so I'm going to get C 6.162 divided by 1.234. I'm going to get H 8.571 divided by 1.234. And then I'm going to get N 1.234 divided by 1.234. Okay, so let's do the first one here. C 6.162. So I'm going to go 6.162 divided by 1.234. And I get C 4.993. And then I'm going to go to H. H is going to be 8.571 divided by 1.234. Which gives me H 6.945. And then N is going to be 1.000. All right, since these are measured values and there's some uncertainty here, you know, what we're going to do is we're going to round this. And so if we round 4.99 to the simple whole number, it's going to be C5. And then H, rounded to a simple whole number, will be H7. And then N. And so this is the simplest whole number ratio. Simplest whole number ratio. The simplest whole number ratio is called the empirical formula. Okay, what we do is we stop here if we have a lattice structure. For example, sodium chloride, we just want the simplest whole number ratio. 1 sodium, 1 chloride. Calcium carbonate, same thing. 1 calcium, 1 carbonate. And so if we have a lattice type structure, we stop here. If we have a molecule, if molecule, or if molecular, then we want to continue. So for example, if we analyze this liquid, and this liquid turned out to be hydrogen peroxide, we sent out this for chemical analysis, it would come out H1O1. But is that the correct formula for hydrogen peroxide? No. That would just be the simplest whole number ratio, H1O1. The correct formula is H2O2. H2, so it's twice as big. So what we have to do is, if molecular, we have to do an extra step. If molecular, must measure molecular mass or molar mass. Or 2, molar mass. Molecular mass would be U per molecule. Molar mass would be grams per mole of molecules. They're the same unit, same number. And so this, well, how do you measure the mass? What instrument can you use to measure the mass of atoms and molecules? The mass spectrometer or some other technique. There are other techniques that we can use. All right, and so what we have to do is, not only do we have to send out the sample for chemical analysis, we also have to get somebody to weigh this. Let's say this is molecular. How do I know it's molecular? Well, it consists of all nonmetals. If it's consisting of all nonmetals, and if it's not ammonium or something like that, then I'm thinking that's molecular. And so this is looking molecular to me. And so we'll send it out for mass measurement. Mass spec analysis. And so when we do that, let me give you the number here. My book doesn't do it. One molecule comes back as 162.12 U. So a molecule of this unknown, you know, what they can do is they can just feed it in the mass spectrometer. The mass spectrometer is going to break it up into individual molecules, and those molecules can be weighed individually. And so it comes back as 162.12 U. And so what we have to do is we have to compare now. Compare the empirical weight with the molecular weight. Okay, I'll call it the empirical mass. What is the empirical mass? Well, we have 5 carbons. 5 carbons is 5 times 12.01 U. I'm going to leave off the units because it's either U per atom or grams per mole of carbon atoms. Then we have 7 nitrogens. 7 nitrogens is 7 times 101. Here I'm only going to take it to 3 because I just need 2 decimals. When I add this up, I'm going to get my 4. And then, 7 hydrogens, sorry. 7 hydrogens, and then we have 1 nitrogen. 1 nitrogen is 1 times 1401. All right, so 5 times 12 is 60, 70. 60 plus 70, 60 plus 70, 70.05, is that correct? Then 7 times 101 is 707, and then we have a 1401. And so that's 5, actually, let's go with this. 7, this would be 8. Actually, let's go this way. 8, 13. 0, 7, 4 is 11. 91, 13. Did I get that right? 81?
That's 60.
Okay, 60. Sorry. That's right. 50 plus 10. And 60 plus 10. 60. So 81, 13? Yeah. So we compare the empirical mass with the molecular mass. And so a molecule of this actually weighs 162.12 U. And so, you know, what we have is half a molecule here. Do you see that? You have half a molecule. So then we take the molecular mass divided by the empirical mass. And then we get this multiplication factor. And so a molecule of this weighs 162.12 U, and the empirical mass is 81.13 U, and so that comes out to 162, actually 0.12 divided by 81.18, 1.997, which is just going to give us 2. In other words, the molecule is 2 times bigger than the empirical unit. Molecule is 2 times bigger than the empirical unit. So what we're going to have to do is we're going to have to double it. And so our empirical unit again was C5H7N. This is the empirical formula. And then we're going to get the molecular formula, which is going to be 2 times that. And so it's going to be C10H14N2. So a single molecule of this has 10 carbons, 14 hydrogens, and 2 nitrogens. And that would be 1 unit of this. This turns out to be nicotine. Nicotine. So once we have the formula, we can determine some properties of this. And we haven't talked much about these organics yet, other than some carboxylic acids, some alcohols, that kind of stuff. The organics, we look at it structurally. You know, when we're looking at this, we're looking for little structural units that tell us a lot about the properties, as well as the composition. What we've been focusing on are the inorganics. And so let's see what time is it. Let's take a look. Is this going to work for me? Okay, maybe that's it. So this is a difficult problem here. Fructose is the sugar found in honey and fruits. It is commonly known as fruit sugar. Its percent composition is 40.0% carbon, 6.71% hydrogen, and the remainder is oxygen. So we could figure out how much oxygen there is because it all has to add up to 100%. And so the difference between the carbon, hydrogen, and 100% is the percent oxygen. The molar mass of fructose, so they give us the molar mass in grams per mole, which is the same as U per molecule. And so 1 molecule of fructose weighs 180.16. Find the empirical and molecular formulas. And so they basically go through the same process that we did. We assume a 100-gram sample, just to review here. You assume a 100-gram sample here. You convert those into moles, get the mole ratio. Here they got it into the simplest whole number, the empirical formula here. And then compared the empirical mass with the molecular mass to get it. And so the factor that they got was 6 in this case. So the molecule is 6 times bigger than the empirical unit. And so this is the way they did it. They put parentheses around here and did this sub 6. I just multiplied it. So my setup is just a little bit different there. So any questions on this? All right, that was the last part of the chapter 7 that I wanted to talk about. The formulas are so important for understanding not just numbers, stoichiometry, but also for understanding this, which we're getting into now, chemical reactions here. And I said, how many types of chemical reactions are there? How many types? Anybody recall? If you look at patterns of chemical reactivity, there were three types. One was kind of a funny name, metathesis. Another was acid-base, and the third was redox, or oxidation reduction. Those are the three types. When you look at this, like chapter 8, how many types do they have here? This is not a complete list. They're missing a lot. They have they have one type called combination, and then another type called decomposition, and then the single replacement, double replacement. So 1, 2, 3, 4 types. But it's missing a lot here. And so if you go to our supplement is more comprehensive. If you take a look at the supplement, Chem Compact, whatever, B, Chem Compact G, how many types do you find in there? A lot. But even then, you know, it's still missing, and it's still not done upright. And so that is okay. You could memorize these, but you know, if you're missing stuff, hopefully they just give you stuff that's here. Like for example, if you memorize these and I throw in another reaction that doesn't quite fit this pattern, then you're going to be stuck. And so it's okay if we just limit, you know, okay, these are the types excluding all these others, and just forget about all these others and just limit to this window, and then you're okay. You know? But if you kind of want to broaden it, then we'll look at maybe categorizing these a little bit differently. And so this is what I'm trying to do with these three categories, is to make it a little broader. Because if you narrow your scope, then do you know what you're missing? It's fine if you know what you're missing, but most people don't. Well, anyway, let's first talk about chemical reactions. You know, this is what we're doing in lab today. What we're looking at is evidence of chemical change. You know, when a chemical reaction occurs, the identity of substances changes. That's the definition of the chemical property. The chemical property is the substance is going to change. And so one thing we can see is the color change here. This is not completely mixed. You're mixing something together, it's creating this color here. From here, this is colorless. We have a colorless liquid. Actually, we have a term for colorless liquids. You know, if it's clear, clear does not necessarily mean colorless. Clear just means you can see through it. And so we could have colored solutions that are clear, like a clear blue solution, you can see through it. This is a clear colorless solution. Clear colorless solutions, you can see here on the left, are abbreviated CCS. CCS for clear colorless. This is clear too, because we can kind of see through this, you know, but it has a color. And over time that color fades. So this is some evidence of reaction here. Color is very tricky though, because the color, it might not be a chemical change, it could just be dilution, you know, or some other thing. So color is very tricky sometimes. You know, was that really a chemical change or was it a physical change? You know? But this is definitely evidence of a chemical reaction. If you're dropping a liquid into a liquid and you get this cloud formation, do you know what that cloud is? That cloud consists of tiny, tiny crystals of solid. In other words, it's called, what was that called? Precipitation. Precipitation is when you have this cloud formation here. Those tiny crystals are floating, suspended like that, but eventually they're going to settle down to the bottom of the test tube. That's just upon the initial formation. Over here you can see like an Alka-Seltzer tab in water, and that bubble formation. The bubble formation we call effervescence. And so precipitation, effervescence is a very common. here we could see evolution of heat and light. Evidence of reaction. Heat and light. Emission of light may not be a chemical reaction. Emission of light, some things like tungsten, like in the old light bulbs, emit light without undergoing a chemical reaction. In fact, you don't want any chemical reaction. And so this is why light bulbs are designed the way they are. You know, metals are easy to oxidize. And so you have to protect the tungsten in a light bulb. How do you protect the tungsten in a light bulb? You keep out the oxidizers. And so what's one common oxidizer? Probably the most common oxidizer is oxygen in air. And so in order to keep out the oxygen in air out of a light bulb, you have to fill the light bulb with some other gas, alternate gas. And so light bulbs emit light, but they don't undergo a chemical reaction. It's a physical process. We'll talk about that more later. And so this might not be. Heat, though, just heat alone without light is evidence of a chemical reaction. You know, so, or cold. This is a cold, instant cold or instant heat packs are definitely chemical in nature. Here we have sodium reacting with water. I showed the video of sodium, didn't I? Did I? Yeah, this is smaller amounts, so we don't see this huge flame erupting. It could pop and explode, but they're reacting it slower. Usually, when you have out of control reactions, those usually result in explosions. Okay, then we have chemical equations. That's what this next section is showing. So, for example, with sodium, when it reacts with water, this is what happens. And so we try to think, you know, what are some chemical properties of sodium metal? How many types of chemical reactions are there? Three. There's metathesis. So does sodium have metathesis properties? Well, what were metathesis reactions characterized by? I forgot to post the chart. Metathesis reactions were called ion switching, right? Or favorable ion combinations. So when we look at sodium, is sodium an ion? Sodium is not an ion. Sodium is a neutral element. There's no charge on it. Therefore, there's no metathesis. So let's skip metathesis. Next type of reaction we looked at was acid-base. The sodium, do you recall seeing sodium? Because we read through the entire acid-base chart, the little one that we had, not the, there's a bigger one, but did you see sodium on the acid? Is sodium a good proton donor? H donor? Is sodium a good H acceptor? Skip acid-base. That leaves us with the final type of reaction, which was redox. Where did you see sodium before on the redox? Do you recall seeing sodium on the redox chart? Well, if not, then maybe, you know, what we need to do is, this is what the best thing to do. Best thing to do is just every once in a while just read through the entries. You don't have to have them memorized. You just read through it, so in your subconscious you might have seen it before. Did I see that before? And you might remember something. For example, I asked you to memorize two species on the redox. The strongest oxidizer. Do you recall what the strongest oxidizer was? Lithium. Or fluorine. What was the strongest oxidizer? Or did I go through this?
I think you did. It sounds familiar.
It sounds familiar. Okay. Did I thought we had the name on everything on the chart, but maybe I didn't. Well, anyway, this is break time, so maybe it doesn't sound familiar yet. But this is a something called descriptive chemistry, and descriptive chemistry is has been emphasized less and less in chemistry. And so chemistry's turned more and more towards physics and less towards chemistry, which is chemical reactions. And so we'll do some more descriptive chemistry so you can get a feel for some of the reactivity or behavior of some of these things. And so let's take a break and then we'll